Okay, so welcome back to this next video in which we are discussing product groups. Okay, right, so we've now discussed how to construct a product group, and we've also investigated the interpretation of what a product group actually means. Okay, what I want to do now is do an example of constructing a product group and interpreting what it actually means. Okay, now the example we are going to do is going to be where you multiply the group C2 with itself, basically. So we're going to construct C2 cross C2. Okay, so firstly what I want to do is remind you of the group C2, because obviously we're going to need to have that fresh in our mind to be able to do this. Then what we'll do is we'll actually construct the product group C2 cross C2, and then what we'll do is actually interpret it, and we're going to see that this is actually going to be isomorphic to a group that we've met in previous videos in this playlist, specifically the Climb 4 group. Okay, right. So first let me just remind you of what C2 actually means. So this is the cyclic group of permutations on a set of two elements. Okay, so this is the group that consists of two elements, and these two elements are going to represent the cyclic permutations of a set of two elements. Okay, so remember how you construct the cyclic groups. What you do is you firstly create a set with the same number of elements in it as this number down here. So we're doing C2, so we only need two elements in our set here, so we might as well go for the symbols 1 and 2, as indeed I have done here. Okay, and then what we need to do is think about the cyclic set permutations of this set of two elements. And what we need to do is give those cyclic set permutations names. We need to give them symbols to denote them, and we're going to then put those symbols into a set, and that set is going to form our group C2. So firstly, let's just discuss the cyclic set permutations of this set of two elements. Now this is very easy because there's actually only two set permutations in total of a set of two elements. Okay, so there is the identity permutation, that's certainly a cyclic permutation. Okay, and then the other set permutation of a set of two elements is the one where you swap the two elements around. So 1 goes to 2 and 2 goes to 1. Okay, the transposition set permutation, and that's also a cyclic permutation. Okay, this is effectively where we're moving everything to the right, or indeed the left, you could view it, by 1. We're moving everything over by 1. So 1 goes to 2, 2 would go to 3, but there is no 3, so we fold back and 2 ends up going to 1. Okay, so these are our two set permutations of a set of two elements, and they are both cyclic set permutations. Okay, right, so we're going to give them symbols as usual, so we'll call this set permutation the identity, so I'll just denote it E here, okay, and then we'll call this set permutation tau, okay, for transposition. Okay, now what we're going to do is we're going to put those two symbols, the identity and tau, into a set, and this is the set that's going to form our group C2. So we put the identity and tau, these two symbols representing these two set permutations of this set of two elements, into a set, and this set is going to be the set that underlies our group. Okay, now of course we also need a composition law on this set of symbols, and that composition law is going to relate to the composition of the set permutations that these symbols represent. So this is very easy to do. Let's just draw out a composition table here. We'll call it abstract composition. Okay, we'll give each element a column in this composition table, we'll give each element a row in the composition table, and quite simply now all we need to do is define all of these 4 entries here. Okay, so firstly we can do this column and this row very easily, because whenever you compose the identity set permutation with another set permutation on either side, it always just gives that other set permutation back again. So the identity composed with identity is just going to equal the identity composed with tau is just going to give tau, tau composed with identity is just going to give tau, and then the final non-trivial one is tau composed with tau. If you do the transposition twice, of course, that ends up coming back to being the identity, because when you swap 1 and 2 around twice, overall the net effect is that you haven't swapped them at all. Okay, so it just becomes the identity map. Okay, so here, and I'll highlight it all in yellow, this is our group then, the set of symbols, those two symbols there, with this composition law defined on it here. So this is C2, and now what we want to do is construct C2 cross C2. So I want to product C2 with itself, basically construct a new group which is going to be C2 cross C2. Okay, so the first thing to do then is to construct this as a set, basically. Okay, so firstly we want to construct that set, which is going to consist of all ordered pairs of elements from the two groups. Okay, so let's go through this. So I want to construct the set of ordered pairs little g prime, where little g is an element of C2, okay, and little g prime is an element of C2. Okay, so C2 here is the first set, C2 here is the second set, or rather groups. Okay, so I want to construct this set. So there aren't that many combinations because our group C2 only has two entries, two elements. Okay, so let's construct this set then. So the first obvious one is that we'll have the identity with the identity. So we'll have the ordered pair EE, so where we put E in both sockets. Okay, we'll keep the first one the same now, okay, and then switch the second one, so we'll get the identity in tau. Now what we'll do is switch the first one, and we'll have tau and the identity, and then finally we'll switch the second one again to tau, and we'll have tau tau. And those are all possible ordered pairs that you could possibly construct, where the first entry is from C2 and the second entry is also from C2. So those are all the elements then in our product group. Okay, so this is the set so far. Now what we need to do is obviously define a composition law on this. So we need to create the composition table, and I think I'll try and squeeze this in down here. Okay, so we need to define what any two elements from here composed together is equal to according to that component-wise composition which we talked about in general in previous videos. Okay, so firstly let's give every element of the set a column and a row in the composition table. Okay, so just putting all of these down here to give them all the column. Okay, so here's tau tau, and now what I'll do is give them all the row as well. So I'll put the identity here, the identity tau here, tau and the identity here, and tau tau here. Okay, and now what I need to do is go through and fill in all 16 of the entries here, and again we'll just call it abstract composition here. Okay, now colour this composition table in red because this is the composition law that I'm defining on my new product group. Okay, so firstly 7 of the entries here are quite nice and easy. Okay, the ones in this column and the ones in this top row are the easy ones because we know that this identity element, that's going to be our identity in this new product group. So that needs to compose with everything to give the other thing back again. Okay, so we can quite simply fill in this column and this row. So the identity composed with identity will just give us the identity back again. Okay, this one composed with this one will give us the identity in tau back again, so just this answer. Then we'll have tau, the identity here, tau tau here. Okay, and then the same thing up here. So the identity composed with identity tau will give us identity tau back again. Identity composed with tau identity is equal to tau identity, and identity composed with tau tau again will give us tau tau. Okay, right, so those are the nice simple 7. Now the other 9 are more difficult. Okay, we're going to have to think a little bit more, but not too hard. Okay, so let's start off with this entry here. So we want the identity in tau composed with the identity in tau. Well, we do this component-wise. So we firstly compose together the identity and the identity here to get our first entry should be the identity. Then we compose tau and tau together in our group C2, and of course there we get the identity back again. So our second entry here is also going to be the identity. Okay, and we continue on. Okay, so next one here we'll have tau and the identity composed with the identity in tau. Tau composed with the identity firstly. Okay, that will give us tau back again. The identity composed with tau will give us tau in the second position as well. Next, down to here, we'll have tau composed with the identity in tau. Okay, so we'll firstly compose tau with the identity, that'll give us tau. Then we'll compose tau with tau, that will of course give us the identity back again. Okay, next column over here, so we'll have identity and tau composed with tau and the identity. Identity composed with tau will give us tau as the first answer, tau composed with identity will give us tau as the second answer here. Next one down here, we'll have tau composed with tau as our first entry, that'll give us the identity, and then we'll have the identity composed with identity, that'll give us the identity as our second entry as well. Next here, we'll have tau composed with tau, that will give us the identity in position 1. In position 2, we'll get tau composed with identity, that will give us tau in position 2. Okay, next, this column here, we'll have the identity composed with tau, that will give us tau. Then we'll have tau composed with tau, that will give us the identity. Next one here, we'll have tau composed with tau, that will give us the identity. Then we'll have the identity composed with tau, that will give us tau. This one, final one here, we'll have tau composed with tau, that'll give us the identity, and tau composed with tau again, that'll give us the identity again. So there we have now worked out our full composition table of the elements of this product group of C2 cross C2. So now that's the construction then of a product group, specifically this product group of C2 cross C2. What I would now like to do is discuss the interpretation of this group, and that will allow us to see that in fact this group C2 cross C2 is actually isomorphic to the Klein 4 group that we've seen in previous videos. Okay, so I want to talk about how we can think of C2 cross C2 in terms of set permutations of some set. Okay, well we know how we do this in general. Okay, we know that we need to take the two sets for the two groups, okay, and we need to union them together to get the set that we can think of the product group elements as representing set permutations of. Okay, so our two groups here are both the C2 group. Okay, so the elements of these two groups that we have producted together, they can be thought of as representing set permutations of these sets of two elements. Okay, now it is helpful to think of these two groups as representing set permutations of sets with different symbols in. I said this when we were going over this more generally, that it's helpful to think of the set SG and SG prime as having intersection 0 basically. Okay, so at the moment we would like to think of both of these as working on this same set. But what I'm going to do is I'm going to think of the second one as working on a slightly different set. So this one here, I'm just going to change the symbols. Okay, so I'm going to think of it, instead of acting on the set 1, 2, I'm going to think of it acting on the set 3, 4. But in essence, the set permutations are exactly the same. Okay, so the identity in this second C2 will just represent the permutation that sends 3 onto 3 and 4 onto 4. And again, the transposition set permutation will represent the set permutation which swaps 3 and 4 around, like so. Okay, so the set permutations here are exactly the same. I'm now just viewing the set that it's working on as being slightly different, and that will be very helpful in interpreting what the elements of this product group actually represent. Okay, so we know what we do now. We just union these two sets together. So we're going to union the set 1, 2 together with the set 3, 4 basically. Okay, and of course what we'll end up then with is the set 1, 2, 3 and 4. And you see now why I had to change those symbols, because if I'd left them as 1 and 2, then of course we'd have hit problems. But so just change the symbols basically. Okay, it doesn't actually change the way the group works. The composition table and the group elements is exactly the same for this. They're just now working on a different set. Okay, so just change the symbols so that the two sets are non-overlapping, and we have this beautiful new set now. Okay, so what we can now do then is interpret all of the elements of our product group as representing set permutations of this new set. Okay, so let's go then. So let's firstly start off with the identity. What does that actually represent? Okay, well, let's think this through. So we'll have our entire set here, and we're going to map it back onto this entire set. Now the entry in the first position here, this tells us about how we're going to send 1 and 2 basically. It tells us where we're going to send 1 and 2, and of course we're going to send them back onto 1 and 2. So you remember when we were going through the interpretation, the first entry tells you about how to permute this subset, SG, and the second entry tells you how to permute this subset, SG prime. Here, the subset SG is the subset 1 and 2, okay, and the subset 3, 4 is the subset SG prime, effectively. Okay, so the first entry is going to tell us that 1 needs to go onto 1 and 2 needs to go onto 2. Okay, so it's going to tell us how to permute this subset. The second entry will then tell us how to permute this subset, so it will tell us to send 3 onto 3 and 4 onto 4. So this entry now in our product group represents the identity permutation of our entire new union of these two sets, basically. Okay, so that's excellent. Next, let's do the identity in tau, and then we're going to be able to fit this in. I'll have a go. Okay, so we'll have the identity in tau next. Okay, so once again I need to draw out my entire set, 1, 2, 3, 4, twice. Okay, now this first entry here, again that's going to relate to this subset 1 and 2, and again that will tell us to send 1 onto 1 and 2 onto 2. Now this second entry here, tau, this tells us that we need to swap 3 and 4 around, so it relates to the transposition of this second portion, 3 and 4. Okay, so that now is what this second element of the product group is going to represent. Okay, right, next entry in our product group, tau and the identity. Okay, so once again I'll draw out my set, 1, 2, 3, 4, twice, like so. And now what mapping is tau, the identity, going to represent? So the first entry is tau, so that means that we need to swap 1 and 2 around. The second entry is the identity, that tells us that we need to keep 3 and 4 the same. Okay, so this now is the set permutation on the set 1, 2, 3, 4 that element's going to represent. And now just enough space for the final element of our product group, tau, tau here. Okay, what is this going to represent as a set permutation of this set 1, 2, 3, 4? Well, the first entry tells us we need to swap 1 and 2 around, and the second entry tells us that we need to swap 3 and 4 around. So this one represents the double transposition here. Okay, and now if you have watched my video on group isomorphisms, you will remember that this is exactly how we built the Climb 4 group. Okay, we looked at these 4 set permutations of this set containing 4 elements, and we saw how if we give symbols to represent these 4 elements and form a group out of it, build a composition table, it does actually form a nice group. Okay, so what I have just shown you is that here we are just using different symbols. We're using these more complicated symbols here to represent these set permutations, but of course the composition law here just relates to the composition of these set permutations, because as we discussed, in general you can always think of this way that we have defined composition of these ordered pairs as representing the composition of these set permutations that we've talked about, that we can interpret the elements of a product group as representing. Okay, so this composition table now just relates exactly to the composition of these set permutations that I've drawn here. Okay, so indeed all I'm using is different symbols to represent these set permutations, but the group structure, the algebraic structure that I've actually got here is exactly the same. So I could find you a relabeling map, an isomorphism between this and the Climb 4 group that we saw in the video on group isomorphisms. Okay, so indeed C2 cross C2 is isomorphic to the Climb 4 group, which is usually written capital V like so. Okay, so that's a nice place to end this video on product groups.